Okay, boundary condition define how the bending stress formula are highly dependent on boundary condition. Okay, boundary condition define how the end of the part are restrained, as well as the position of the load and whether it is concentrated or distributed across the surface of the part. Okay, tengok table seterusnya, table yang ni. Okay, table 3.5 give stress and deflection formula. Okay, stress and deflection formula for the bending of beam with different boundary condition. Okay, ini adalah boundary condition awak tengok ada yang dia letak dekat hujung sini, ada yang dia letak dekat tepi ni. So the symbol P, okay ni P, denotes concentrated loads, okay, in Newton ataupun pounds, and the symbol W denotes loads evenly distributed across the beam, okay, which is given by newtons over millimeter or pounds over inch. Okay, we use the value in a table yang mana yang tadi, table yang tadi kita guna value dekat table yang ini, okay, untuk tahu value I and Z. Okay, for accurate result, use the secant modulus or apparent modulus for E. Okay. Dekat sini saya tak bagi contoh calculation. So tak apalah, tak payahlah. Ke korang nak belajar kira-kira ni? Sebenarnya tak perlulah kot. Okay, design for stiffness or part shape. Untuk design for stiffness, kita dah cover sebelum ni. Dan dalam soalan test pun pernah keluar soalan. Okay, for designing for stiffness, you can use a variety of options to improve part stiffness, including overall shape, wall thickness, ribs, and material selection. So dekat section ni kita akan discuss the other option. Okay, first option is the part shape. In many applications, the overall part shape is the predominant design factor, which is affecting the part stiffness and load carrying capabilities. So taking step early in the design stage to select a good basic shape, we can avoid expensive or the troublesome measures in the product developed to achieve the desired strength and stiffness. So sebelum awak design tu, awak kena tahu shape tu mesti dia boleh elakkan daripada sebarang masalah lah. So for selecting the stiffer shape, seldom add significantly to the final part cost. Okay, kena consider juga dia punya cost. The advantage of the design flexibility in the molding process to maximize the stiffness of your design. So we need to consider crowns or corrugation for large surface. Okay, crown around the surface to form a slightly domed shape that adds considerable stiffness with little additional material. Okay, we can see this is the crown. Okay, this is the corrugation. For example, the corrugation that can add stiffness to non-cosmetic parts. So, figure ni dia tunjukkan the effect of crown. Effect of crown ni lah, crown dia punya shape dia macam ni. Okay, effect of crown height on the stiffness in a circular disc supported at the perimeter. So this is the graph, shows the relative stiffness, which is stiffness dome divided by stiffness flat. Okay. So it is plotted against the ratio of dome height to disc diameter. So the different curve represent that this diameter to this thickness ratio. Okay, ni diameter ni height, ni stiffness, kan. So for the example of a 10-inch, okay, 10-inch diameter disc with a 0.1 inch wall thickness, we see that adding a 0.25 inch dome increases the stiffness by about 300%. Okay, next. Okay, lagi satu yang ni. Okay, the figure ni is the adding curvature to the side wall, enhance stiffness and appearance. Okay, so long unsupported edge, such as those on the side wall of box-shaped parts, exhibit low stiffness. So they also tend to warp during molding. So kita kena letak curvature to the side wall. So by adding the curvature to the side wall, it will increase the stiffness and reduce the hourglass shaped warpage during in box shaped parts. Okay, dia letak curvature. So design for this figure. Design permitting straighten unsupported edge with a stiffening profile. Okay, so preferably a straight drawn profile that maintain the uniform wall thickness and mold without side action mechanism. So when possible, use other component of the assembly to provide the additional stiffness. Okay, yang ni dia lagi stiff lah. Okay, plastic housing often contain rigid internal components such as cooling fan, metal shield, and heat sink, which could add support to load bearing surfaces. Okay, ni figure the hollow shape of this lost core manifold at both function and high rigidity. Okay. Generally, difficult to mold via conventional method, hollow profile can provide a high level of stiffness. Okay, ni part yang hollow kat dalam. So, the lost core process, okay, kita panggil the lost core. Okay, lost core, they use lost core process to manufacture the engine manifold part shown in this figure lah. So it will employs a sacrificial low melt temperature core to mold intricate hollow shape. So the hollow section function both as an air duct and also as a stiffening members that withstand the load and vibration of the application. Another process for producing similar hollow part is the multi-shell process, form hollow shape from separately molded parts which are joining later by welding or overmolding. Okay, this is the figure about the gas assist channel. So gas assist channel, a growing technology which has high pressure gas is injected into the melt stream behind the flow front to produce hollow section. Okay, this process can create networks of hollow channel for stiffening. So this is the hollow channel. This hollow channel, it can augment stiffness in weak areas such as unsupported edges or provide major support in areas subject to high load. So biasanya dia akan letak dekat tempat yang tak ada supported. Okay, kalau yang ni ada supported. Okay, so dia boleh bagi stiffness lah. Dia boleh bagi support juga. Okay, for wall thickness, because the stiffness is proportional to thickness cube, relatively small increase in thickness can reduce deflection greatly. So a 25% increase in thickness nearly double the stiffness of a simple plastic surface. While adding more thickness to improve stiffness is a simple solution, it is not always practical. Okay? So although they generally offer excellent strength to weight performance, most parts made of plastic will have to have wall thicknesses several times greater than other common structural material to achieve the same stiffness without geometry changes. So in reality, molding and economic factor limit the available wall thickness range for stiffening. Because of the molding related issues such as shrinkage stress, packing difficulty, cycle time, um, so the practical thickness limit well below to 0.25 inch for most solid thermoplastic. Because good molding practice calls for uniform thickness through a part, a local need for additional stiffness often result in an overall thickness increase, which is adding both part weight and cost. So kalau kita tambahkan tambahkan wall thickness, weight dia akan meningkat dan juga cost pun akan meningkat. So the table here gives the wall thickness relationship between the various material and steel to give the same deflection for a given load. So the equivalent thickness factor, which is ETF, listed in the table, assume that a flat shape and short-term loading at room temperature. So the table shows that to have the same stiffness, a flat shape would need to be 4.4 times thicker in polycarbonate than in steel. Okay, so um, to estimate the equivalent thickness of other material or material combination, kita nak estimate equivalent thickness of the material ataupun combination of the material between plastik ataupun metal, kita kena kira dia punya equivalent thickness by this formula. Okay, T is the thickness and E is the appropriate flexural or tensile modulus. Okay, ni contoh soalan calculating equivalent thickness. Okay, if an existing aluminium part is 0.03 inch thick, what thickness does an identical part make? So if of part made of, okay, ni sambungan sebenarnya. Sorry. Part. So try kira macam mana cara dia. The equivalent thickness awak akan dapat value 0.062 inch. Okay, awak masukkan nilai yang tadi. Cuba kira. 0.03 darab dengan 10 kuasa 7 bahagi dengan 1.116. Okay, awak akan dapat nilai dia 0.062 inch. So calculation of equivalent thickness for long-term loads or load at temperature other than room temperature should substitute the appropriate creep modulus or secant modulus value for the current and proposed material. Okay, this is the ribs. Okay, ribs, as we know, ribs provide a means to increase stiffness without increasing wall thickness. Okay, figure 3.2. Figure yang mana Kita tengok figure yang ni dulu. Asalnya dia adalah flat. Dia tak ada rib. Lepas tu dia letakkan rib ni. Adding a rib double the part stiffness with much less material than simply increasing the part. Because they are usually thinner than the main wall section, ribs seldom add to the molding cycle time. So rib also adds stiffness selectively in specific area and direction. Okay, figure ni dia tunjukkan common rib design for chair base members. Okay. The deep U shape, it provide primary strength and stiffness. Okay, untuk yang Yang ni